a little bit about Eigen to kick things off. Eigen was founded in 2012, and we're based in Fredericton, New Brunswick. Not exactly a manufacturing hub, but we have an amazing engineering school at the University of New Brunswick, and that's actually where we have our roots. We are a combination of machine learning, AI, and engineering experts that have been really focusing on helping manufacturers derive the ultimate amount of value they can from machine vision solutions. And over the course of the last few years, where we've really dedicated our focus is to thermal inspection. So helping manufacturers using thermal processes use thermal imaging and AI to inspect every product they make in line. And essentially, today we're going to be focusing on automotive plastics, but you will see that we are using those thermal applications and thermal inspections across different applications as well. So without further ado, I'll talk to the guys that are the experts that you're here to see, and I will turn it over to my colleague, Josh.
Thanks, Scott. And welcome everyone to this webinar. So to get started, I want to give a quick overview of the technology here that we built at Eigen that powers our thermal imaging plus AI inspection solutions. So we've been in business for over a decade, and we've used that time to build some pretty comprehensive technology. And just so briefly, so this technology allows us to do inline quality inspections using thermal imaging on an edge device deployed in a factory that makes real-time decisions. So this edge device, and you can see it in the middle here, does all the data processing. It connects to the cameras, it connects to the PLCs, it runs algorithms and performs logic operations to make real-time quality decisions on every product that is being manufactured. To this edge device, we also have an HMI screen that allows operators to see the inspection in real time in the factory. And this screen also allows for inputs of quality labels that we can feed into our AI models, all done within the factory. Another key component of the solutions that we provide are that they are hybrid solutions. So there is this edge component that does all of the real-time execution and decision-making, but we also upload all of the data to a cloud platform, so our OneView cloud platform. And this allows us to have full traceability of inspection data, much more capabilities in terms of analyzing and exploring data. It also allows for remote management of these solutions. And the other key aspect of the cloud platform is it is where we train our AI models and manage AI models across one or even more machines. Next slide, Scott. So in this talk, we are going to focus on thermal imaging and the considerations and advantages of thermal imaging. But before we dive into thermal imaging, I want to talk a bit more about imaging in general and how cameras capture and process data. So to keep this general, we'll just first look at the electromagnetic spectrum. And so we can see here that for shorter wavelengths, we're looking at things like ultraviolet light. Going a little bit above that, we start to get into visible light. Going beyond that, we're now in the infrared light. And above that, we get to microwaves and other things. But most of us are familiar with color cameras and visible light. It's what humans see, it's what we interpret. So we'll start here. So cameras measure light at specific wavelengths. And color cameras have 3 different types of pixels: red, green, blue. Each pixel is sensitive to certain wavelengths, And you can see the sensitivity in the plot shown here. So every pixel measures light according to those wavelengths, and the intensity of light corresponds to the value of the pixel. And for color cameras, these red, green, and blue pixels get interpolated and converted to a specific color. So now let's move to infrared. You can go to the next slide, Scott. So going from visible to the infrared space, infrared gets divided into 4 different categories. We have near infrared and shortwave infrared. And these are useful for certain things that inspections that absorb and reflect light. So a lot of use cases in quality inspection for NIR and SWIR are things like looking at fruit and vegetables and identifying rot, things that are subsurface, because these objects emit that light, reflect that light differently. But going forward into the mid-wave infrared and long-wave infrared, now we're looking at heat that objects emit. So not that they reflect, not that they absorb, but that what they actually emit. So this takes us into the thermal imaging domain. And for us, we mostly focus on long-wave infrared. You can go to the next one, Scott. So long-wave infrared is really the wavelengths that a lot of industrial thermal imaging cameras operate at. So that 8,000 to 14,000 nanometer range. Our partners, like our hardware partners like Optus and FLIR, the cameras that we deploy for customers for quality inspection are all long-wave infrared. And similar to color, so these pixels are sensitive to a certain wavelengths. And the intensity of a pixel in these cameras gets converted to an actual temperature. So these pixels generate thermal images that allow you to see and use temperature in your inspection. Now let's go to the considerations. So thermal imaging is great. It can do a lot of things for quality inspection, but there are considerations that you need to pay attention to in order to properly use these cameras for inspections. And the first thing to note is that these cameras measure the infrared energy emitted, transmitted, and reflected. They can't isolate emitted energy only or transmitted or reflected. They see all 3 sources. So the application that these are used for, you really need to determine if you're looking at emitted, transmitted, or reflected heat sources, because that will impact what is actually visible within the image. These cameras typically operate in the range of -20 Celsius up to about 1,000 Celsius. And there are different ranges within that the cameras can be set to. The other important thing to note about thermal imaging is that every object has an ability to emit infrared energy. And this is called the emissivity of the object. And emissivity is a fairly complicated thing. It is a function of the material. It is a function of the texture of the surface. It is a function of the color. And it's also a function of the viewing angle of the camera relative to the object. If we look at the table on the right-hand side, we can see emissivity values for different materials. So things like polished metal, polished aluminum, have very low emissivity. So these act more as reflection rather than an emissive source. So getting an accurate reading on temperature of something with very low emissivity can be quite hard. However, when we go forward and we look at things like plastic, for example, we have emissivity values that are much closer to 1, which is the maximum value, which means that we can get a much better reading of the emitted energy of an object. And an ideal black body actually has a value of 1. So that's the highest you can actually achieve. So emissivity is complicated because it's a function of different things. So what we normally focus on with the solutions that we deploy are solutions that are best for comparing relative temperature measurements. So things that part over part show differences in terms of the temperature profile in the image, but that you don't need accurate absolute temperature measurements. You can achieve accurate absolute temperature measurements, but they're simply hard because of the emissivity values. They need to be set correctly. And when you have different objects, different materials in your image, it becomes more and more challenging to do. So comparing relative temperature measurements is definitely the best way to proceed when possible. And lastly, thermal images just inherently have lower resolutions. So these cameras are more expensive than color cameras. They have lower resolutions, but they provide very valuable data sources that allow for quite complicated defects and quality considerations to be identified. But related to resolution, we do recommend in most cases that you maintain about a 10:1 pixel to smallest defect ratio when you're deploying these systems. So the smallest defect that you want to identify should be at least 10 pixels in size. And as long as that is satisfied, our algorithms to identify defects normally will work quite well on those features. So now let's talk about the advantages of thermal imaging. So thermal imaging is quite a powerful technology in that it allows us to see invisible thermal data that humans simply can't see. And this thermal data can be generated by the process itself in most cases. So there is no need for active heat sources, which actually makes these cameras quite easy to apply to existing operations. These thermal cameras can also see defects both on the surface of the part, looking for different types of surface defects, but also inside products, because the heat profile of the image changes depending on internal properties. So looking for things like voids in plastic parts has a very good use case of thermal imaging. The cameras are also relevant for both continuous and discrete manufacturing applications. We do support both in a variety of domains today. And they're used to not only detect defects, but also to monitor production in real time. And the technology that we built on top of thermal cameras allows us to do this with rules and with AI to really push what these systems are capable of. I'm going to briefly cover where we've been in terms of machine vision and where we're going at Eigen. So conventionally, machine vision systems are rules-based systems that are really restricted to the types of problems that you can easily constrain with rules. Can I set a lower limit on my temperature, an upper limit, that sort of thing. These systems are primarily standalone, so it's a single camera doing a single inspection that really has limited source of data for that decision making. And the data, there's also very limited access for many of these systems. So trying to access an image, trying to access the data to better understand what's going on and use that outside of that vision system is very limited, very restricted. So at Eigen, what we focused on is enriching these systems with AI. So our solutions are AI-powered defect detection systems. We still use rules where they're relevant, but AI first in most cases. Also support not just a single camera making an isolated decision, but multiple cameras connected together that combine that data with process data to make a much more informed decision about what's going on and what quality decision needs to be made. And lastly, and as we talked about before, so we have both an edge component for real-time execution, but also a cloud component that consolidates data, exposes data, and provides much more rich analytics on that data to improve overall understanding and really drive preventative actions within the operations. I'm going to briefly summarize how our system works, and then we're going to dive into a video that will show what our product actually looks like. So we have our industrial edge kind of as the centerpiece of all this. And this collects data, it captures data from the line. And this can include historical data, data from PLCs, data from cameras, data from sensors. All of that gets ingested and used for decision making real time in the factory. The HMI connects to this to expose the user to the results in real time. And all of this data can also be uploaded to the cloud for traceability or explainability. The edge device makes the decision, and then it can also report the results for automation back to the line. So communicating with PLCs in order to trigger rejections, to actuate robots, all of that is supported within our product. We're going to show a quick video here of our OneView cloud product. Here we're looking at Algorithm Builder. So this is how we deploy and configure custom algorithms on these edge devices. It's all block-based, lots of capabilities in terms of what we can do. There is full traceability. So every algorithm that gets deployed is fully traceable and can be rolled back if any issues actually occur. Here we're looking at our monitor interface, which summarizes all of the inspection results by 30 days and 24 hours. Next, we're going to look at our Explore interface. This is really what shows all of the detailed results. We can look at the values within the thermal image for understanding what's going on. We can look at all of the data that gets ingested. We can configure data to show custom plots per user. This gives better explainability of what's going on in order to drive preventative actions. And we can also do all the labeling. So we can label good, fault, and defect for AI model training within that interface. With labeled data, we can jump to Model Builder. So this allows us to build out these AI models from all of those labeled data. We can train different types of models. We can review training reports in order to understand what the performance expectations are. And these are all configurable by the user to adjust the thresholds to configure their throughput according to the application. So that's a very quick overview of our OneView product. We'll be happy to answer any questions that you guys will have related to that. And let us know after the call if you're interested in seeing any additional demos related to that, and we'd be happy to jump on a call. So there's lots of capabilities. Questions, Scott?
No, I was just going to jump in. We have a few questions that we've received. So just before we transition to James's content, as long as you're wrapped up, Josh, I thought we might tackle these questions.
Perfect time.
Excellent. Sorry, one sec. I think Jacob, I think you had your hand up here. I'm going to unmute you and go ahead. Oh. Okay, can't hear you there. I'm not seeing your hand up anymore, but we did have a couple questions through the Q&A. And one of them was, can you keep client data related to learning local, i.e. client data and related model dev isn't used to enhance solutions by competitors?
So our strategy, when we collect data for a customer, that data is owned by that customer. It is held privately on the cloud by that customer. So we do only use the cloud for model training, but the data from the customer is owned by the customer. So the models that result from that are used only by that customer. So we're very strict on what we do with our data when it is collected.
And then another question was, what typical improvements do we see in waste, fewer false versus defects, and product output, fewer false plus defects, if that makes sense. If not, I think.
So let me just clarify what we mean by fault. So we have three main categories that we use today. We have good, which is simply the object, the product is good. We have defect, which there is a defect. There can also be specific types of defects. We do support both. Fault for us is when there was an issue with the decision making. So this could be there was a miscapture from the camera. There was something that occluded the image, occluded the part, so that we couldn't make a good or a defect decision. We do support all three. Ongoing model refinement allows us to improve the accuracy of the model and reduce false positives and false negatives over time. So our models, our AI models that we deploy, they do not stop at the first deployment. They are something that continually evolves over time.
And just one last question, which is interesting timing considering that some of our colleagues are on the road. Do you have a portable version that can be used for site inspections?
We do, and we'd love to bring it on site if you're interested in seeing how thermal imaging can work for your use case. So reach out after this, and we'll be happy to set up a visit.
Great. I think that's all the questions I'm seeing in the Q&A right now. If there aren't any others, then we can switch over to James.
All right. Good morning. We're going to dive now into a bit more of an applied discussion for the rest of the session. So take what we've covered in the first part and look at some of the specific places that we've provided thermal imaging solutions with AI, specifically in the automotive industry, and even a little bit more narrow than that. Automotive plastics is one of the leading areas to develop solutions with this type of technology. And you'll see actually in the next slide here, there's quite a wide range of places that this can be really relevant. So plastic welding is one of the biggest use cases. We'll cover three different examples within plastic welded automotive components. We'll look first at fuel tank welds, then on to welded rear lamps, And then from there into interior parts, like in instrument panels, glove boxes, or door panels even. There's also all kinds of other thermal processes, things like hot stamping, adhesives for windshields or for interior components, functional testing like rear window defoggers or seat heaters. So lots of different places that we can apply thermal imaging within the automotive industry, in particular within automotive plastics. We'll go now into a bit more detail on welding specifically. Before I do, here's a couple of just snapshot images from our platform. You can see, again, some of the plastic weld examples. The windshield adhesive example we'll talk about in more detail in a few minutes. That's in the bottom left. There's an image of a spot weld here. And then you can also see some of the more transition type inspections where thermal imaging is really good for in an injection molded part, for example, for short shot or flash, or maybe warp detection. But then if you wanted to add surface inspection to that, we certainly have the ability in the platform to support other imaging types. You can see an example there where we've added a 2D optical type camera for surface inspection, along with the thermal inspection we're doing on a part that's immediately released from the mold. On to plastic welding in more detail. So I said we'll talk through a few different use cases, kind of high level components that are safety critical or components that may have higher instance of potential warranty. Think rear lamps when you're driving down the highway and you see a lamp that may have partially filled with water. Those types of things where they're sealed parts or parts that should be sealed are really good use cases for leveraging thermal imaging with AI to verify that you're actually getting both a good weld and a properly sealed part. So the first one, next slide. Looks like it's frozen. Oh, there we go. So the first one we'll go into in more detail, automotive fuel tanks. So this is one that we're really excited about. We've been working in this space for a number of years. And if you're not familiar with these parts, essentially what you're seeing in the bottom left, it's a plastic valve which gets welded onto a blow molded tank. And the process that's most typically used is hot plate welding, where the components are preheated and then fused together. And we've developed a really innovative solution that looks at those preheated components to predict the quality of a weld joint. We've used this in a number of different plastic weld applications. Fuel tanks, of course, being a safety critical part, are a really compelling one. And one of the things that these solutions help unlock, it's not just about the defect detection or risk mitigation, but it's also the ability to help mitigate physical testing or destructive testing that's often done by manufacturers to validate the welds on this type of product. So this is a use case that I mentioned we've been working with this customer for a number of years. We've scaled this across many machines at this point. In the plastic welding space more broadly, not just fuel tanks, but fuel tanks, lighting, interiors. We've deployed these solutions on more than 40 welders at this point and seen really good scalability of models. And we're going to talk a bit more about that in the lighting example. Next slide. So before I go into the lighting example, a quick snapshot of what this actually looks like in our platform. So the operator experience, Josh gave you kind of a tour of the cloud platform earlier, and really that's what's shown here on the right-hand side, where you see kind of a daily dashboard that, oh, let's go back, there we go. You see a daily dashboard with anomalies, faults, and defects from production over the last 24 hours, and then a quick view to all of the defects or faults that were identified in that period. So that's all available on a cloud level, and we do have reporting that's generated on a daily and weekly basis for customers as well. But in terms of line side, in virtually all of our installations, there's an HMI that's typically installed at the line, and that view in the top left here gives you a sense of what that looks like on the floor for an operator, where they're seeing the results from the latest part produced, but can also see some of the history from, in this case, about 10 parts there, and you see green check marks on those that were validated as good, and there's a little red part in there that would have been identified as a defect. So that's all available at the edge on an HMI for the operators to understand what may have happened or why a particular part is being rejected. We'll go now into the plastic welding use case for lighting. Very similar to what we covered on fuel tanks. This is a highly scalable solution. Once we've worked through building out what we would refer to as the virtual image, to get appreciation for that, you have to think through the complexity of the part. So these automotive tail lamps are not typically a flat surface, and they're not typically something that can be inspected with a single camera view that allows you to see the entire weld profile. So in most of these stations, we would have multiple cameras, and we actually leverage the part CAD along with the different perspectives from the different cameras to build an overall weld profile of the part. So what you're seeing in this central view here is a weld profile that's been built from multiple camera perspectives. And on the next slide, you'll actually see what the construction of that looks like. So in this case, the 3 different camera perspectives on the left-hand side, the normalization process that we go through, and then you can actually see that 3D texture mapped part view in the center white block there. Why this is really important is all back to how do we scale these solutions so that we don't have to start from zero when we go to the next welder. So we typically would train our models on this type of normalized data set, which really does enable the scalability of a solution to another welder, which may be a different part. It may be, a different part with a similar weld, with cameras in different positions. Because we're working with this type of normalized data set, we can actually generally get the inspection on the next machine, to a fairly high confidence level, so that you're only doing refinement as you scale across the factory. You're not having to go and start and develop models from scratch on each machine. So that's one of the things that has really helped us unlock a lot of value with customers is how do you start to scale these solutions more quickly once the initial one has been deployed. Another example, so we've covered fuel tanks, we covered lighting. This one is an instrument panel weld. for an automotive interior part. Again, certainly looking for cold spots or abnormalities in the weld, and then also, once again, supporting the reduction or elimination of destructive testing. The next slide, we've got a few more examples. So I mentioned functional testing, so seat heaters or rear window defoggers. We talked about interior parts with instrument panels. Here you see both glove boxes and door panels. And then finally, injection molded parts. We'll go into a little bit more detail on this, on the injection molded case study, and then the next slide. This is actually probably a good one to go back to one of the questions from earlier about how to help mitigate false positives or false negatives. So in this solution, what you're looking at, it's an automotive B pillar. It's a plastic injection molded part with a high appearance requirement as a visible part on the exterior of the vehicle. So this one's a two-part solution for us, where one is thermal imaging for looking at things like short shot or potentially part warpage. The second portion is more of the surface inspection, looking for read-through and splay. Now, read-through and splay are highly subjective defects, and they can have, certainly a small amount of splay, or anything between that small amount and a large amount that's very visible. So when you think about a defect like that has a certain level that would be acceptable, and anything beyond that you'd want to reject, those are the ones that are really at higher risk of having a number of false positives or false negatives. And as we work through the model training that Josh was describing earlier, there's ways that we can really help refine the thresholding around kind of part clusters that enable you to reject what you want to reject without necessarily impacting the throughput in production, which is obviously paramount. So really interesting solution for the plastic space that's two-part, both thermal and optical. The last one that we've got for today is an adhesives example. So we've done a lot of work with thermal imaging in different adhesive applications. This one in particular is an automotive windshield. So looking at the consistency of that adhesive bead on the windshield, looking for things that may be variation in temperature, variation in profile, could even be relative position. So another potential high value use case where certainly windshields need to be properly sealed as they're installed in the vehicle, and traceability of this type of data is highly important to the manufacturer. One kind of final view before we close. So we've talked a lot about automotive today, but we do provide solutions for a number of other verticals as well. We've done a lot of work with thermal imaging in paper and packaging industries. Think like paper production, or box adhesive to extend on the adhesive example from the windshield. Then also in various industrial segments, I think things like metal welding of large structural grates, or even some recent interest in thermal imaging applications for the food industry. So the same technology can be utilized in a lot of different verticals. And you can see here on the left-hand side the sheer volume of images that we process on a daily basis, and this number is actually low. I think we're in the 3 to 4 million range now. So we've got really well proven solutions that our customers depend on. And to leverage the quote that's up in here, it really does help change the type of work that team members are doing on the floor every day when they've got much more intelligence into the process or product that is being monitored. I think now we'll turn it over to questions. We may have actually seen another one pop up here while.
Yeah, there was one that popped up, James, and that was just asking if we've met any resistance from the shop floor on the testing solutions in terms of impacting job security or union concerns.
It's not something that we've encountered frequently, but I mean, certainly it is something that we have seen, and particularly in one highly regulated industry. So definitely a concern that can be raised, but we've been able to navigate those with leveraging the data and the solution on the floor to help augment what an operator is doing, rather than necessarily view it as a threat for replacement. And I think that's proven to be kind of a good transitional step.
Great, and I think there was a few questions that we received just from people that couldn't join us this morning, but one was, is there any specific examples of a company using the product traceability that you were talking about earlier?
Yeah, it's one of the things that we didn't maybe highlight as much as we could have, but certainly going well beyond just the traceability that you get in the part records that we have. It's the searchability of the data within the platform. So if, for example, you've been notified of a customer event where you've shipped parts to a customer and a customer's encountered something that maybe it's not even a known defect. It's some type of anomaly that they're concerned about and they want to understand exposure on. It's very easy to go back into the platform, do a quick search for defects that would be similar to whatever is being reported by the customer, and go and isolate those particular parts or images to help with containment, so that the customer is not having to go and search through thousands of parts in inventory to try to find a few parts that may have been impacted. So that's definitely something that we see customers using our platform for, and we're actually constantly working on ways to more quickly analyze the data to help deliver value for those type of containment actions.
Great. Just in being conscious of time, I will throw it back out to the audience here to see if there are any additional questions before we wrap things up. Great. I'm not seeing anything come through the chat or any hands raised. So thank you, everyone, for joining us this morning. And I will be sharing a link back to the recording of this session if there's anything that you want to review again. And of course, if you have additional questions and want to talk more, we're pretty excited about the demo that Josh mentioned earlier. So if there are specific questions that you would like answered, then feel free to get in touch with us. And there is additional information on our thermal solutions on our website at eigen.io. So with that, unless James and Josh have any last